So two talks. The first one is Felicitas Hörmann, thank you very much, about some security consideration for McEliece-like Cryptosystems based on linearized codes. I have to read all of it.
Yeah, it's a very long title. Thanks for the kind introduction. So welcome also from my side, and as Eduardo said, we are talking about some considerations for McEliece-like cryptosystems in the sum-rank metric, which haven't been proposed yet. So let me quickly show the outline of the talk. First of all, I will give an introduction and also motivate why we are actually considering that. Then I will continue with some preliminaries that we're all on the same page concerning linearized resolving codes and the sum-rank metric. Then I will introduce a distinguisher for linearized resolving codes, which then also impacts the security level of such a cryptosystem. And finally, I will give a short conclusion and an outlook on future work. So let's get started. The classical McEliece cryptosystem was proposed in 1978 for binary Gopher codes and the Hamming metric. And as we have already heard several times today, classic McEliece is a round 3 finalist in this post-quantum standardization. And the major drawback of McEliece is that it has large public keys. And in fact, for 128-bit security, so category 1 in the standardization process, comparable to AES 128, is 261 kilobytes. So for that reason, we really have to do something and improve the key size. One idea to do that was actually to switch to another decoding metric. And the rank metric has been considered because the generic decoding problem is harder there as in the rank metric. So this means that we can actually use lower parameter sizes to achieve the same level of security. And that was the idea of the GPT cryptosystem by Gabidulin, Paramanov, and Tretyakov. They used Gabidulin codes, but as it turns out, that system was broken several times and also repaired, and there was a lot going on. But Overbeck's attack is still a problem. So the attack consists of a distinguisher for Gabidulin codes, because most of the time we have this public generator matrix and it looks as if it was random. But if we're able to distinguish it and really find out the secret parameters of the Gabidulin code, we already broke the system. So what do we do here? I have already told you the classical McEliece system is in the Hamming metric and the GPT system is in the rank metric. But there is also one metric that actually spans the whole spectrum, and that's the sum-rank metric. In the rank metric, we have Gabidulin codes. They are the analogs of Reed-Solomon codes. And in the sum-rank metric, we have linearized Reed-Solomon codes, which contain both Reed-Solomon codes and Gabidulin codes as special cases. So it has already been shown that generic decoding in the sum-rank metric is somewhere between generic decoding in the Hamming and the rank metric. Of course, we can reach both extremal cases since they are included, but I mean, it makes sense that we try to also establish a cryptosystem based on the sum-rank metric, because maybe we can do better than the Hamming metric in terms of the public key size. But maybe we can also avoid some attacks that work in the rank metric, because maybe they don't apply to the more general setting in between. And moreover, if we choose linearized Reed-Solomon codes, then we have lots of parameters that we can choose compared to Reed-Solomon or Gabidulin codes. So for that, we get a large space from where we can choose our secret code, which makes it harder to actually find out the secret. At least that's the theory, and that's why it's interesting to look at a McEliece-like scheme based on linearized Reed-Solomon codes. Exactly. Okay, so let's quickly recall the main idea. So we have a finite field FQ of order Q and an extension field FQ to the M of degree M. Then we have Alice, who wants to send a message X, which is an FQ to the M to the K. And she encrypts it by multiplying it by a public generation matrix. And she adds a random error vector E of a given weight. Then this is transmitted over an insecure channel, and Bob receives it. And if he knows the secret, then he's able to recover X. So what is actually there is the private key, which is G, a generated matrix, in our case, of linearized resolving code. And we have an efficient decoder that is able to correct errors up to some rank weight T. Then we have a row scrambler, which is just a random dense non-singular matrix. And we have an isometry that is applied from the right-hand side to G, which is called P here. And the public key is then obtained just as the product of F of S, G, and P. And we also add to the public key the error weight T, because Alice has to know how many errors, or an error of which weight she is allowed to introduce. Okay, and we can decrypt that successfully because we can just apply P again to XG pub plus E, which is the received word. And then we obtain, kind of a transformed error E times P. But since P is in sum rank isometry, we keep our sum rank weight. And since we know the decoder, we can decode it. So that's the main idea. And we will talk about this system in this talk. And I will give some considerations, what we have to think about when talking about security of such a system. So first of all, let's get a little bit into the detail of the sum rank metric codes. And for that, we consider a vector X of length N. We divide it into L different blocks Xi, and they all have length Ni. So if I add up all the Ni's, I will get N. And then the sum rank weight of X is defined as the sum of the rank weight of the Xi. So the rank weight is the maximum number of FQ linearly independent entries of Xi, which is actually the same as the rank of the matrix that I obtain if I use Xi and I expand each entry column-wise with respect to a fixed basis of FQ to the M over FQ. Okay, so here we can clearly see that the sum rank metric actually really generalizes the Hamming and the rank weight, because if I divide my vector into n different blocks, so each block has only length 1, I get the rank weight, the Hamming weight. And if I use the whole thing as one block, I get the rank weight. And I can use this weight to introduce the metric, of course, by just using the weight of the difference of two vectors. And linear sum rank metric code in our context will be an FQ to the M linear subspace of FQ to the M to the N. Okay, then I already told you that linearized resolving codes are such sum rank metric codes. In order to define them, we need an FQ linear automorphism on FQ to the M, and we need a sigma derivation. For simplicity, I just wrote down an explicit formula because it's easy to write it down in the case of finite fields. So delta is just some gamma from FQ to the M times the identity minus our automorphism that we chose. And we also need the concept of conjugacy classes. So FQ to the M gets partitioned into these classes if I consider one element and all its conjugates. And by a conjugate, I mean actually a to the c equals sigma of c times a times c to the minus 1 plus delta of c times c to the minus 1. And c of gamma is called the trivial conjugacy class because that only has one element and the others have more elements usually. Okay, and if I have that, I can define the operator dA of b for all a's and b's in FQ to the M. And it is just the automorphism applied to b times a plus the derivation of b. And we use that to now define the linearized resolving codes. For that, we need code locators beta I. So for each beta I, we have beta 1 up to beta ni. And we need some evaluation parameters that are now from different non-trivial conjugacy classes, because then we get nice results with respect to skew polynomial evaluation. So that's a little bit of the theoretical background that I don't want to go into detail here because of the time. And then we can define a linearized Reed-Solomon code just as the row space of this generated matrix I wrote down here. So we take all our code locators, then we apply the operator with respect to the evaluation parameters for the different blocks. Then we apply it once more and so on, up to applying it k-1 times, such that we get a code of dimension k. So this code can also be written as an evaluation code. So when you're familiar with Reed-Solomon and Gebiet codes, they can be written as evaluation codes for normal polynomials and linearized polynomials. And for linearized Reed-Solomon codes, we actually need skew polynomials, and their evaluation is not unique. So there are different ways of evaluating them, but in this case, we would use generalized operator evaluation. So basically, that is based on this operator that I put here in the generation matrix. Okay, so the question is, if I have a generation matrix, a public one, that looks random, how can I find out if it is the generation matrix of a linearized Reed-Solomon code? And for that, we consider this nice operator gamma that depends on a set of evaluation parameters. And we can apply it to a matrix M. So we have, again, our L different blocks of the matrix. And we apply just the operator with respect to the different evaluation parameters per block. So we basically do the same as in the generation matrix, but this time to the whole matrix element-wise. And there is a conjecture which is very similar to the one in the rank metric by Overbeck, that if I take a random full rank matrix in FQ to the M k times n, and I also assume that the blocks have full column rank over FQ, but that is more of a technical thing, then the rank of gamma aj of M is at least the minimum of j times k and n with high probability. So yeah, as I said, the condition that the blocks must have full column rank is basically only for a more detailed analysis that I don't want to go into detail here. But if you do simulations, it also works for full rank matrices that don't fulfill that, because most of the time that is fulfilled anyway. Okay, but what happens if we apply this operator now to the generation matrix of a linearized Reed-Solomon code? So this is the generation matrix, as I have shown before. And if we apply now our operator, then we apply it once more, basically. And we can see that all the blue rows in the top are also there in the bottom. So if we consider the rank of this matrix, we only have to take into account the orange rows. And those are k+1. And we can also see that the last row is actually just the continuation of the generation matrix. So in fact, we can see that gamma A of G has FQ to the M rank k+1, and it generates the same linearized Reed-Solomon code, but this time of the dimension k+1. This is just an example. I can continue doing that more often. So if I use a generation matrix G of an LRS code, and I apply this operator j times, then I get FQ to the M rank k+j. And actually, this matrix generates the code with the same parameters, but with dimension k+j. So this means that actually, if I know the correct parameters, the evaluation parameters, then I can find out if the matrix represents a linearized Reed-Solomon code or not, just by looking at the dimension. But in fact, if we have zero derivation, it is sufficient to know the correct conjugacy class of the evaluation parameters. So I don't have to know them in detail. I can just use the conjugacy class, because then I can just basically get this diagonal matrix D, and I can put it out, and basically that doesn't change the rank. So I'm sure here. For that, I have to just cancel out the first row of the operator, but it works nicely. You can just, if you look at it, it's really clear. Now the question is, what happens if we actually try to disguise this LRS code? And as I have shown before, we use isometric disguising here. So our generation matrix in this case becomes iota of G times P. Iota is just for semilinear isometries and P is for linear isometries. It doesn't really matter. I just wanted to put it down correctly because we can express semilinear isometries as a matrix. So in the sum-rank metric, it means that we are allowed to permute blocks of the same length, to multiply blocks with an FQM scalars, and to multiply them from the right with invertible FQ matrices. And I can also apply FQ to the M automorphisms element-wise. If I do that, then a crucial observation is that GPUB is still a generalized linearized Reed-Solomon code, which means that I get a linearized Reed-Solomon code for which the columns can be multiplied with FQ to the M elements. So similar to generalized Reed-Solomon codes. And this means that if I want to distinguish this code, like the LRS code that has been disguised with an isometry, then I only have to figure out the correct column multipliers B, and then I can apply my old distinguisher, because then I get just a normal regular LRS code. And yeah, actually that is very helpful because we can figure out a strategy to recover the secret key if we use this McEliece system that I showed earlier. Because we saw that the operator, if we apply it, we generate a code, the same LRS code of a higher dimension. And we can do it up to the case where we generate the code of dimension n-1. And then we can just use the dual code and compute the code locators from there and compute back the code locators of the secret code. And of course, I have to put a little bit more effort in there if I want to do that as well for disguised LRS codes, but it's doable. Just as a quick outlook, because I think I'm running out of time already. So yeah, basically what I've shown you today, I've shown a distinguisher for generalized linearized Reed-Solomon codes. So we considered linearized Reed-Solomon codes with column multipliers. And this impacts the security of a McEliece-like system based on these codes when we allow row scrambling, which doesn't change the code, and FQ to the M semilinear isometrics disguising from the right-hand side. That was our matrix P, and also applying automorphisms element-wise. And what we still want to do is a more detailed analysis of the conjecture's success probability. If you remember, I showed you that for random matrices that the rank is higher as for LRS codes. And we want to do that, to analyze that more thoroughly. Then we also want to generalize this setting to near isometries. So we will also want to consider some other disguising mechanisms. For example, just adding columns or something. Then we want to derive a key recovery attack. I just quickly sketched the idea before, but as I said, we have to take a little bit more into account when we also want to recover the key for really disguised systems. We also want to study other distinguishers for these kind of codes, because, for example, for Reed-Solomon codes, there is the sure product distinguisher, and it might be interesting to see if that carries over, and if so, if it actually is the same distinguisher or what we get. And of course, it's also interesting to analyze cryptosystems in the sum-rank metric in general. So, for example, in the rank metric, there is Ladro's rank amplifier scheme, and it would be interesting to see if that works out in the sum-rank metric as well. So that's it from my side. Thank you very much for your attention, and I'm happy to answer any questions.
I'm not sure if I understood the isometry correctly, the characterization of the isometry correctly.
Should I go back?
Yeah.
You mean this one?
So do you basically apply the isometry per block and then allow permutations of block at the same time? Would that characterize it as well?
Well, actually, it should, because I mean, you take the sumrank metric, and if you, I mean, the blocks are basically just rank metrics, more or less. So if you take rank metric isometries in the blocks and you also allow permuting them, it should be the same, yeah.
You said that the hope is that the tags known for the rank metric do not like transfer to the sumrank metric. Did you have closer looks into this and say transfer?
Yeah, actually, like this is an attack that transfers. So the overback distinguishers from the rank metric for the Biddle encodes, and this actually shows that it transfers. But of course, okay, you have to know the evaluation parameters, or at least their conjugacy classes. So for that reason, it is a little bit more costly than in the rank metric, but the main idea carries over.
And I'm not super familiar with the text on rank metric, but are these texts which led to this huge drop of security levels of the proposed rank schemes that made them fall out of this competition? Because this was this algebraic effects. I'm not sure if these are the same effects as you were considering here, because for these effects, I think it would be crucial to know if they transfer.
Yeah, that's definitely right. I'm afraid I'm not following that into detail, so I'm not sure which tags actually caused the drop, but it's definitely interesting to look into them. Thank you.
So for having metric codes, for some analysis of actually you can often reduce them to the rank metric code that you're stating that coordinate and see them as a diagram, right? Yes, you could do the same thing for some rank metric code, does that help you with reductions? What problems would you use in structure for that?
I mean, the problem is that you know that the Hamming weight and the rank weight always have the inequality, but for the sumrank metric and the rank metric, it's the other way around.
So you could just map all the components to the diagram. What they are, you can rank it.
Ah, yeah, okay. Okay, now I understand what you mean. I understood you, but I mean, yeah. I mean, it's an interesting approach. I haven't seen it, but maybe it's worth having a look at that. I mean, it seems reasonable.
Yes. Sort of like a bottom line. Do you think this is a promising avenue for building secure systems, or will there always be a distinguishers?
I guess it's promising, but we shouldn't only use isometries. So we have to think about some more advanced distinguishing techniques. The question is if they work out in some rank metric better than in other metrics, which has to be seen. But for example, as I told, in the rank metric, there is this rank amplifier scheme that still works. So maybe this works in the sumrank metric as well, and maybe we can even gain a little bit security because we have this large amount of parameters that we can choose. But yeah, one has to have a look at that in detail.
I think we should thank Felicitas again, and actually